Welcome back, everyone. In this lesson, we will extend our knowledge of finding volumes of solids of revolution. And this time, we will focus on the method of cylindrical shells. So this is really, it's basically a neat technique for where we would usually need to integrate with respect to y. It's a different way now to be able to do it with respect to x, okay? So to kind of build on the concept here, okay? Let's suppose we have some region over here, and we're going to revolve it around the y-axis. So I'll draw my mirror image. And, in our previous lesson, we discussed disks and washers. So if I was to draw that in here, we have this purple function wrapping around, we have this blue function wrapping around, and I would classify these as dy washers. Okay? Well, the method of cylindrical shells is now just gives us a different way of visualizing this region that gets made up. So instead of actually taking, some point on our function and actually rotating it around the axis, what we're going to do instead, I'm going to take a vertical slice from my original region, okay, and I'm going to wrap that around the y-axis. So my mirror image is going to look something like this, and again, I am going to get like a circular shape here. But now it's this entire region that's being rotated, and what we get is what's known as a cylindrical shell. Okay, and I can take a slice anywhere. I could take this vertical slice and I could wrap it around, and I'm going to get what's known as a cylindrical shell. Okay, what a cylindrical shell is basically a cylinder without a top or bottom. Okay, it's just the outside of it. Think of like a empty paper towel or toilet paper roll. Those are cylindrical shells. Okay, they have no tops or bottoms. Okay, and what we can think of then is that this solid region that we get at the end of the day is made up of an infinite number of these infinitely thin cylindrical shells that are basically nested inside one of another, creating this region. Okay, so again, it's a very different visualization of how we're filling in this region, but the idea is that we have all these empty tubes or these cylindrical shells that are stacked within one another that create this overall region, okay, until we get to the end here. And so it's like we got all these things sitting in each other, and the process is the same. Like with disks and washers, what did we do? We basically found the volume of a single infinitesimally thin washer disk, and then we used integration to sum up all those values over the interval. And it's a similar process here. We're going to come up with the volume of a single infinitesimally thin cylindrical shell, and then we're going to integrate over our set of bounds to add up all of those volumes, giving us the volume of the overall region. Okay, so let's start with a cylindrical shell to begin with. Basically, a cylindrical shell, if you were to take like an empty paper towel roll and you were to cut like straight up it on one side and then unwrap this thing, you'd be looking at nothing more than a rectangle. Okay, a cylindrical shell is just a rectangle where these two sides have been rolled together to connect. Okay, what's the area of a rectangle? Certainly that's base times height. Okay, so here's the height of our shell. The base, when I roll this thing back up, is nothing more than the circumference of that circle. So the area of a cylindrical shell, I'll just call it a shell, is, well, what's the formula for circumference? 2 pi r, so we've got 2 pi r times h. Okay, now in terms of relating this back to some arbitrary function, okay, let me clean this up a little bit. Okay, here's our mirror image. Okay, and again, let me draw like one of these in. So here's one vertical slice that I've wrapped around, creating this cylindrical shell. Okay, so 2 pi is just a constant. We're going to leave that alone. What I need to do is figure out how do I get r and h in terms of my function in the variable x. Okay, so the blue function is our f of x here. Here's my original set of bounds from 0 to this value. I'll just write it from a to b. Okay, and so think about it. If I want the radius of this green cylindrical shell, I mean the radius is just going, if I rotate around the y-axis, this is the radius. The radius is just going to go from the y-axis to whatever x value I happen to be at. So if like that's x equals 1, the radius of that particular shell is 1. If I were to draw another shell in a little further away, that would have a larger radius. Okay, this radius going out here would be, well, let's see, this is 0, this is maybe the x value at 2, that would have a radius of 2. The point is, if you revolve around the y-axis, the radius is equal to whatever x value you are at, okay? So I'm going to replace r with the letter x. The number x, whatever x equals on the interval from a to b, will give me the radius of that particular shell. The heights, right? If I'm at x equals 2, here's the height of that particular shell. Well, that's just the y value of the function at 2. That's literally just f of 2 here. Okay, so the height is given by the y value at whatever x value you're at. That's simply given by f of x. So the area of one such shell will be given as that. Now we want to extend this to volume. Okay, well, what do we need to give it volume? We need a little bit of thickness on this thing, okay? And these do have thickness. Like a sheet of paper has thickness, these infinitesimally thin shells have thickness as well. But the nice thing now is that the thickness is this little change in x from left to right, right? The thickness of these vertical slices are infinitesimally thin, and so we call these thicknesses our dx's. So if I want to give it volume, if I want to find volume of one such infinitesimally thin shell, I would plug in whatever x value I'm at into the function, into that, and then whatever I'm using for dx, okay? And again, we let the number of shells go to infinity, we let dx go to 0, and at the end of the day, we get volume equals. Now, the 2 pi is a constant, so I'm going to put that out in front, and then I want to sum up all the volumes of these things, so this is what we integrate from a to b. X times f of x dx. This is our basic formula for volumes of shells, where x represents the radius, f of x represents the height. Okay? Now, are we always going to revolve around the y-axis? No. And are we always going to have a region directly above the x-axis? Not necessarily. So let's talk, kind of more general terms for this stuff. Okay, let me clean this up a little bit, kind of redraw a diagram. Okay, so again, I'll leave the basic version of the formula down there. Again, this is about y-axis rotation and above the x-axis, okay? But again, what if I have a more arbitrary region, okay? So let me draw something like this. Maybe I have here's this f function, and here below it is this g function. Okay, that's creating some region on some interval. And now let's suppose I wrap around some other line that I'm going to call x equals k. Okay, so some different vertical line that I'm wrapping this thing around. Okay, but the same idea, conceptually, if I take a vertical slice and I wrap it, I've got a set of cylindrical shells here. Okay, so it's still the same idea. It's going to be the 2 pi integral from a to b of our radius times our height. But again, the trick is to get radius and height in terms of our functions, okay? So look, the radius now of this shell goes from the center of the circle out to the x value we happen to be at. Call that x sub 1, So that would be the difference. What's that length going to be? I would have to do what with this number and this number? I'd have to subtract them. Okay, so that's the difference here. To find the radius, we have to subtract x minus the line of rotation, okay? And we always want that to be positive. So the radius basically becomes, it's either going to be x minus the line of rotation, or it's going to be the line of rotation minus x, and it depends on which one's further to the right. When we get into some examples, I'll make more sense of that. But a way that I can get around that for either for now is to say, look, it's going to be the absolute value of the difference in these, okay? So that's what I'm going to sub in for r up here in a moment. in terms of the height, where am I getting the height of this particular shell, this green shell? Well, the height here is the difference in the y values between f and g. So the height here would be given by f of x minus g of x. And so if I sub those in, the more general is 2 pi integral a to b. For the radius, we're looking at the absolute value of x minus k. That's the radius portion. For the height portion, we're looking at the difference in the functions f and g. And there's our more general version of the formula, which I'll scroll down and I also have rewritten, okay? It's right down here at the bottom of the page. So the volume of shells, 2 pi integral a to b, absolute value of x minus k. That represents the radius of the shell. F of x minus g of x is the height of the shell. Now, if the region's right above the x-axis, then g of x is just the line y equals 0, okay? And we get back this more simplified version of the formula, okay? But let's go through a few examples here, and again, hopefully you get the setups, and then again, be careful punching things into the calculator using Math 9 if you need to, okay? So let's go back to an example we looked at yesterday, which was actually the e to the x minus 1 function on the interval from 0 to 3. Okay, we did this yesterday, and in fact, if I quickly look, you know, we can see what we got in the disks washers lesson. Here's the work for it right here, part C, revolve R, this region about the x-axis, and find volume, okay? And so this was the big ugly integral we got. All right, and after I punched it in, I got about 230.411. All right, so again, when we wrapped this originally, we got what we were classifying as dy washers. Well, now the idea is, you know, we can find this same volume, and it shouldn't be quite as much effort. So take a look. I will wrap around the y-axis. Instead of drawing in the washers, I'm going to take a vertical slice. I'm going to wrap that, and I'm going to see that I have shells now. Okay. So method of cylindrical shells. Now notice this is around the y-axis, so the line of rotation is k equals 0, and our original bounds are over here from 0 to 3. Okay, so here's the formula. The formula says, all right, integral is going to be 2 pi integral a to b of x times f of x. Okay, and our region is right above the x-axis, so this is the most simplified version of this type of thing. So the original bounds are going to go from 0 to 3. The smallest circle occurs at radius 0, the largest at radius 3. And then in the formula, x is just the letter x. You don't do anything with that. F of x is the function we're dealing with, e to the x minus 1. And so now this integral should be exactly equivalent to the one we just looked at from the other lesson. And sure enough, when you punch this into the calculator, you get exactly the same end result of 230.411. Okay, so it's a nice method for being able to do something in terms of x, which otherwise would have been in terms of y. You know, and that requires finding inverse functions and y bounds and all that stuff, which is, you know, a little bit more work than we need to be doing at this point, okay? Now let's take a look at a couple more examples where we can see we're going to start like looking at regions between curves, and we'll alter the line of rotation. So in part A, let's take the region between y equals x and y equals x cubed, and we're going to rotate about the y-axis first, and then maybe in part B what we'll do is we'll rotate about the line x equals 1. Now in this problem, I didn't give you the bounds. The bounds are going to be where these things intersect, okay, so at 0, and then we can set these equal and solve for x. And it looks like that's going to be at x equals 0 and x equals positive 1. They would intersect over at negative 1, but we're only focusing on the region in the first quadrant here. Okay, so there are bounds in terms of x from 0 to 1. Rotating this about the y-axis. We'll get this kind of a region, okay? And again, I'm going to take a vertical slice, draw the mirror image, and show that I have a cylindrical shell here instead of using washers. Okay, so again, this is my little dx. The original bounds are going to go from 0 to 1. And we are revolving around the y-axis. So again, the line of rotation is 0. But the region's height is now in between the two functions. The height is going to be given by top, which is x, minus bottom x cubed. Okay, so let's take a look here. Volume equals 2 pi integral 0 to 1. We revolved around the the y-axis, so we leave x alone, but the height is going to be top minus bottom, and there's your integral setup that would give you the volume of that region. Okay, and again, I'm not going to punch these in. You can do that on your own if you choose to. Much more interested in the setups. Okay, now let's take a look at what happens if we move the line of rotation over to the right to x equals 1. And so this is right through here. Okay, all right, drawing one cylindrical shell in. Okay, there it is. Now look, it's still a shell, it's still the same basic concept, but a couple of things. Here's our original bounds from 0 to 1. Notice the line of rotation is to the right of this interval. So I can't do x minus 1 to get the radius here. I mean, think about it. If I want the radius of this particular shell that I've drawn in, if I do this x value minus 1, that's going to come back negative because x is less than 1. And we're not squaring the radii in this formula like we do with discs and washers, so the order of subtraction really matters here. And this is going back to the absolute value stuff I was talking about earlier, okay? Since the line of rotation is to the right of our original bounds, the radius here is going to be given by the line of rotation minus x. Okay, k minus x in this case. So you got to be careful there. Our height is still the blue function x minus the purple function x cubed. So putting it all together, volume is 2 pi integral 0 to 1. The radius is given by 1 minus x. That's this horizontal difference there. And the height was given by x minus x cubed. Throw your dx on at the end, and you've got it. Okay, folks, let's do 2 more examples, and we'll wrap it up and reach out with any questions you may have. Okay, so here I have the region bounded by the vertical line at x equals 1. And I've got y equals ln of x is this. Okay. And I'm going to cut it off at the top here, okay? And I bounded it from 1 to e squared, okay? And we're going to revolve that first around the y-axis and then secondly around e squared. And again, so you can see how we adjust for the radius in these things. So revolving around the y-axis, we're going to get something to this effect. And take a vertical slice, draw in one of an infinite number of these cylindrical shells. Original bounds are going from 1 to e squared, and the bounds are to the right of the line of rotation. Okay, so let's see. Volume equals 2 pi integral 1 to e squared. I'm revolving around the y-axis, so that's just x minus 0 or x. And then again, our height is given by the top function minus the bottom. Well, the bottom function was y equals ln of x. What's this top line? I guess we need to get the equation of that horizontal line right here, okay? Well, what's the clue? We're looking for the y value when x is e squared. So y equals ln of e squared, which is, of course, just the number 2. Okay, so that top line is just the line y equals 2 here. Okay, so the height is given by top minus bottom. Our height then is 2 minus ln of x. And there you have an integral that would give you the volume of that region. Okay? And last but not least, what happens if we take the same region and revolve it to the right around the line e squared? So that's right here. Here is my mirror image. Here is a vertical slice. Volume equals 2 pi integral 1 to e squared, are still my original x bounds. Now, the line of rotation at e squared is to the right of our original bounds. So to correctly compute this length, I take the right value minus the left value. That's going to be e squared minus the x value I'm at. The height is still the difference between the functions, top minus bottom. Throw a dx on the end, and you are all set. Okay, folks, again, some of this stuff's going to take practice. You got to work on drawing these out. You got to get more comfortable trying to visualize these regions. And, of course, reach out with any questions you have. Have a good day, and see you soon.